All right, our next speaker this morning is Necdet, who comes to us from Pomona College. Necdet's been working this summer with Matthias, and he'll tell us about their project together today, Torques on Hot Jupiters.
Thanks, Gwen, for the introduction. So I want to start by showing you an illustration of a hot Jupiter around its host star. So why are we interested in hot Jupiters? Let's first start by the definition of them. Hot Jupiters are hot because they are located very close to their host stars. And they are gas giants that have similar sizes and masses to our Jupiter. That's why they are named hot Jupiters. And because their orbits are much shorter than that of our Jupiter, they have significantly shorter periods. And also they have strong surface magnetic fields. And because of these extreme properties, they are great for analyzing forces that depend on these quantities. So first, let's start by electromagnetic force. So first, because the hot Jupiter is very close to its host star, this proximity drives thermoplanetary winds around the planet. And as a magnetic rotating body, the planet drives these magnetic fields that are normally fixed on the planet to curve. And magnetic field lines have kind of a spiral shape here. And anything in this region, which we consider like planetary winds, are affected by this magnetic field lines, and they co-rotate with the planet. But while doing that, the hot Jupiter itself loses some angular momentum. Therefore, that causes a negative torque on the hot Jupiter itself. And this is called the magnetic rotator theory. Second, this is the gravitational attraction. And because the planet is very close to its host star, some of its matter might expand toward the star. But when the rotational frequency of the planet and the orbital frequency of it are significantly different, then these bulges, these extensions, might lag behind the orientation of this line. And in this case, we consider this alpha as a constant time lag. And right now, we are ignoring any third bodies, any exomoons, and we are focusing on only two-body systems. So why are we using them? Because being negligible in other planetary systems, these two torques, tidal and the wind torque, become important in the case of hot Jupiters. And what do we want to do? We want to first search for a balance between them, equilibria points, and then calculate the time evolution of systems with hot Jupiters with different initial conditions to reach these equilibria, to gain a better understanding of the evolution of rotational and the orbital properties. So first, we have so many parameters, variables that we can change. So I started first by changing each parameter individually. So I saw that changing semi-major axis changes the tidal torque, which are shown here with solid lines. And this line shows the maximum possible tidal torque, and this line shows the minimum possible tidal torque. And then I tried different values for magnetic field, surface strengths, and also semi-major axes, and I found maximum and minimum wind torque values here that are similar to this one. So I want to focus on these two areas, the black area and the white area. I want to see when these two areas intersect or like overlap. And this would mean that an equilibrium is possible. And these two plots are different, but the only thing that's different parameter-wise is the stellar mass. Here we have a 1 solar mass stellar mass in this plot, and here we have 81 solar mass stellar mass. So here I'm trying to actually change the stellar mass and see its effect. But as you can see, we don't see any overlap between these two areas. So varying only stellar mass between these plots does not yield equilibria. So here I'm doing the similar thing for planet size. We have 0.1 Jupiter size planet size here, 2 Jupiter sizes, and 10 Jupiter sizes. But as you can see again, we don't see any overlap. Here, I'm changing the structure of the magnetic field, and I try monopole structure and then the dipole structure. And I'm not seeing any overlap again. So that's why I conclude that we saw that although varying each of these change the torques, none of them is enough to establish equilibrium individually. So I have to change them at the same time, like a combination of them, but not each of them individually. So to that end, I started looking at combinations of magnetic field surface strengths and mass loss values. And here, I'm trying to solve torque equations and inputting different values for these variables to see what velocity ratio I would need to establish equilibrium. So these are the inputs to the equations, and this is the result. Each color shade here corresponds to a value in the rotational velocity to orbital velocity ratio. And this is a log range. So that's an example. I have a typical 1 solar mass star and a typical 0.05 AU semi-major axis. And as you can see, all these values are very, very, very small. They are like 10 to the negative 40, 10 to the negative 30. This means these values are actually approximately 0. I have similar plots here, but now I'm changing semi-major axes and also stellar mass values. I'm seeing some yellow colors, some darker colors, but here, as you can see, the values are still very, very, very small. This is the same figure for dipole situation. And again, the values change, but they are still very, very close to 0. So now I found that I would need almost 0 rotational velocity ratio for equilibrium. So then I tried to see what analytical magnetic field solutions I would need to establish equilibrium. Now I'm doing a different thing. This is a different method. So now I'm changing rotation and orbital velocity ratio and semi-major axes. And for each combination, I'm just inputting them and getting the net torque values as outputs. And these outputs are shown here. And I specifically look for the environment around 0. 0 is shown here with this blue box. And these are larger and these are lower. And I'm trying to change the magnetic field values and plot different plots to see when I get good equilibrium, good points. And to see the zeros here, I additionally plot the 0 net torque values themselves. So these 4 plots are for different 5 plots are for different 5 magnetic field surface strengths. And we see that the zeros vanish here almost completely. And after this point, they vanish as well, but I didn't include them because I didn't want the slides to be too complex. But yeah, I still have almost 0 magnetic field surface strengths I need to establish equilibrium. And that's for the dipole situation. And it's similar. I still have very approximately 0 values. So we saw that equilibrium occurred when rotational frequency or magnetic field surface strength is approximately 0. Since the wind torque is proportional to these 2 parameters, these places are actually when the wind torques are approximately 0 as well. And if our model is correct, we see that the wind torque dominates and that an equilibrium is only possible when it's approximately 0. We also wanted to see time evolution, so I used some equations and the torque equations I previously had. But first, I wanted to test my model. First, I included 0 initial torques. And in this case, we wouldn't expect anything to change because there is no force, no torque. And this is exactly what happened in my model. They stayed constant, which is nice because this is what we would expect it. Here, I have initial 0 tidal torque, but I'm changing the magnetic field so that I have a non-zero wind torque. And I just wanted to see how the model behaves. And because the magnetic force dependent wind torque is always negative, I'm seeing a slowdown in rotational velocity, which I would expect. So this is, again, a nice result. But since I didn't have like good equilibrium points other than zeros to approach, I couldn't really calculate the time scales. But that's the future work. So conclusion, considering a system of star and orbiting hot Jupiter, we calculated these torques. And although varying each of these individually, I couldn't really approach equilibrium. And I saw that equilibrium of the torques occur only around these 0 values. But I talked about the magnetic rotator theory before in the previous slides. Is just might be that it's not really realistic in this range, and we need to find other theories to apply to this range. There are also thermal ties that are similar to the gravitational ties that we do not include in this research, but they might be playing a significant role. And also there might exist other bodies around the systems, such as exomers, that we ignored in the first place. So possible future work are about these. And I can also consider different parameters, like maybe eccentricities as well. Yeah, thank you.
And Necdet, that's very cool work. Thank you for presenting. In some of your contour plots, there were some spikes.
Yeah.
Yeah, can you explain what those are? Like what physically those, yeah, those ones.
These ones, right?
Yes.
So these happen at very large mass loss rates. And they happen around here in the corner. So this means there's a huge magnetic field. So I would guess maybe because the mass loss is so high that the mass of the planet is increasing a lot, or yeah, that's my guess. I don't really know actually. Or maybe I'm changing the semi-major axes from left to right, and we are seeing more wiggly things here at the end. So maybe it's about the distance, and at a large distance, we are not seeing a huge effect of magnetic field. Maybe, yeah.
That was a great talk, Necdet. I had a question about this specific slide and the one right after it. So the bottom left plot, right? In most of your plots, the yellow tends to be in the bottom left. But for this specific plot, it's on the right. And I was wondering if there's a reason why this plot is so different from the other plots. Because if you move to the, yeah, so because if you move to the dipole situation, it's still like similar to the other plots, but then for that specific case, it seems different. So I was wondering if there's a reason why.
I don't really know actually, but it might be because of the specific Python command that I'm using. It's try contour F. And also here we have a very huge stellar mass, like 200 solar mass stars. This is huge. Like maybe this is an extreme case that we get very weird values. So I'm not really sure about that, but I need to check it.
Thank you.
Maybe just to follow up on, you mentioned like you chose a 200 solar mass star. How did you choose the different values for your parameters?
So throughout my presentation, I wanted to see if any chance of equilibrium is present. So I used the most minimum thing I could use and the most maximum thing. So this is like very huge, I know, but I just wanted to like try. I just wanted to see if like this model becomes like realistic, not realistic actually, becomes important in these values. So it's just, I tried the minimum and the maximum. And I also tried values that are between them, but I'm not showing everything here. I have other plots. here, for example, I'm using 1 solar mass, 3 solar mass, 9 solar mass, 27. Yeah,
Most massive planet. So I guess just to follow up, what is the most massive star that hosts a hot Jupiter that we have discovered? Like it can be much more massive than 1 solar mass, I would imagine, right?
yeah.
Okay. So those would be all hypotheticals.
All right, let's take Necdet.